I want to make my talk rather more intuitive, and we want to share a new trends of model that is happening, and we are planning for new kinds of inference interface for those kind of models. And I'm naming this kind of thing the inference engine for multi-stage generative models. Yeah, and thanks so much for my teammates from MC's org and the Astralan Omni team. And I'm on behalf of like 30 people working on the community. Okay, so uh, to be quick, the contents of today, I want to share 4 things to follow the first principle to design an interface. The first thing, like what kinds of model we are optimizing, what's the computing progress they are using, and given their computing progress, what kinds of computing characteristic does it have? The computing characteristic, I guess you have already familiar with the words like mem intensive or like computing bounded or like kernel function or those kind of things. But to our end, I think this kind of thing is purely computing characteristic. And new characteristics should have new serving frameworks to make it quick. And after getting the computing progress and the characteristic bit, what kinds of system do we design to make it quick, adaptable, and easy to use? And the final thing, given the system we have right now, what kind of thing we are working on and where we are headed to. So we can take it go over. Yeah, and uh, the first topic I like to introduce today is the multi-stage decoding. So I here listed 2 models. You may not hearing their words, but I can give you some context. The first one is like the Queen 3 Omni, is yet the best, we call it multi-modality generative model so far. So I can give a concrete idea, like you are using Gemini. Say I tend to using Gemini when I was in in a stack house, since a lot of those kinds of menu I do not know what their means. So I use Gemini and I open Gemini's Omni mode. In the Omni mode, I can turn on Gemini's I can turn on the camera of my phone, and then I can talk in audio to Gemini. So in this sense, Gemini is getting my video and my audio input, and then Gemini like gets my input and think it inside, and then output with me. First, type the text answer to the screen, and the second, he gets audio output. I mean, to pronounce the text output loud to me. So that is Gemini Omni. So as the Kunfig Omni. It is like a multimodality model that supports video, audio, text, and of course, picture input, and give us text and additionally audio outputs. Okay, so that is those all we call it Omni models, and the other models we're optimizing on is like those TTS models. So what is TTS? In short, TTS is trying to like following the sounds to produce another sounds. Give a concrete example. You input your sound to TTS model and you give it a text. Then the TTS trying to use your tone and your motion to pronounce the text given. So TTS model is like purely text to audio model. So those kinds of modalities seems to be new, but underlying those models, they have showing different kinds of inference, or we say like computing progress. We name it like multi-stage computing progress. So the first one, Omni models, is widely saying that Omni models, most of them using the thinker-talker model, thinker-talker architecture. So what is a thinker-talker? Thinker, you can treat it as a vision language model, but thinker continue to put the input because is hidden dimension and is text token to the talker, and then talker try to pronounce the text thinker given loudly. So that is a thinker talker. One used to think and another used to talk, right? It's purely intuitive. But another one, like the slow AR and fast AR. So this is rather less intuitive. So in a short explanation, slow AR and fast AR is like something that put them together, they can put them together. They give the slow AR is like try to decide what the contents of the audio should be, and fast AR is something that used to modify the contents with some verbal, with some emotion, with some tone. So that is slow AR and fast AR. So compared with traditional language models, what's the difference here? Most of the times, traditional language models, specifically, they have only one autoregressive loop. But here, for the single talker, single is autoregressive loop, and talker is another. And the slow AR and fast AR is so far. Yeah, for slow AR is a big autoregressive model, but fast AR is a smaller autoregressive model. In essence, traditional inference techniques we are mostly facilitating those kinds of single autoregressive loop. We have like MTP, we have like continuous batching, and we have like page attention, Redis cache, those kinds of techniques. But directly adapting those kinds of techniques for single autoregressive models inference to here shall not work, since right now we have two autoregressive loop, or even more. So that's the problems we are tackling. And in another sense, we can compare it like this. First, as I said, multi-stage models, they have rather than one autoregressive loop that makes it complex. But most of the models, they still have one single stage decoding, or they even do not have decoding, they only have the prefill, like I said. The diffusion models, they are most like the prefill. So what kind of thing we are specifically talking about to optimize in our framework? Yeah. And here I listed several models that they have maybe similar namings, but they have been tackling different frameworks. The first one is like the MECO Omni and Neutral Omni. Yeah, they have the same name like Kun3 Omni or Min Omni, but they are tackling different thing. MECO Omni and Neutral Omni, they are like adding a new dimension, audio dimension to traditional vision language models, and they do not produce audio outputs. So in this means they only have one decoding autoregressive loop. So they are putting in SGLang. And for the Kun3 ASR, MECO ASR, those kinds of great ASR models, even though they are like working on audios, but still they only have one autoregressive loop. So we put it in SGLang. And another thing is like the WAN model, chicken image model, those diffusion models. Most of the diffusion workload is like denoising, and denoising is nothing related to autoregressive model, but they are like a one-time prefill workload. So we put those kinds of one-time prefill workloads still in SGLang. And the left parts, all those kinds of models with multiple stage or specifically multiple decoding loops, we put it in SGLang Omni. So the point behind this, as I have said, what matters is not the modality. What's the matter is a actual computing progress. The computing progress. If the computing progress to get one output has to run into several autoregressive loop, then those kind of models should be put in SGLang Omni. But if it's still one decoding loop, then we put it in SGLang. Yeah, SGLang Omni is a specific building up framework of SGLang to utilize SGLang's already established techniques like continuous batching, KV cache reuse, those kinds of things to facilitate the multi-stage model decoding. Yeah, and after we get the computing progress, in short, multiple autoregressive loops or multiple stages, what kinds of computing characteristic we have? So the first computing characteristic I want to share is like, as we know, traditionally speaking, we think that prefill is a compute bound progress, and we think that decoding is a memory bound progress, right? So take that into Kun3 Omni. As we said, Kun3 Omni's feature is like a large model that dominates most of the prefill workload. So we tend to say that the feature is computing bounded, and we say that maybe the talker. How about the talker, and how about the MTP layers to accelerate the talker? Indeed, the talker and the MTP layers, they are neither computing bounded or memory bounded. Per workload of the talker and MTP is really tiny. So the real cost is actually the latency, the launching time, the kernel fusion, and the synchronization. If we run all of those into one scheduling, if we use one scheduler to manage the schedule problem of the thinker and talker, it is totally damaged, since we see that the thinker is like computing heavy, but the talker is like a latency sensitive one. So our first design principle is we say scheduling decoupled. Since there's multiple autoregressive loop, we give different scheduler and they use different scheduling policy to facilitate the scheduling of each AR loop. For Quantic Omni, concretely speaking, we have one scheduler for thinker and another scheduler for the talker. Yeah. And the second thing, we call it like communication layer. So, if previously we only have one scheduler, then we do not need to care about like inter-scheduler communication. But right now, different stage have different schedulers. So between those schedulers, we have to design new communication principles. So, concretely speaking, thinker and talker are loosely coupled. The talker reads from a buffer from its own space, and talker and MTP are tightly coupled. So each single step, the talker and the MTP layer is concatenated together. So we put the talker and MTP layers in one schedule. Okay. So in that sense, we design a control plane and a data plane to facilitate the data communication between the thinker and the talker. In short, the control plane using ZMQ to only sending those kinds of communication information like the metadata, like where the data should go to and where the data is from. But the real data is sent from the data plane, maybe most of the time using MECO or using RDMA, those kinds of communication protocols. Yeah. Okay. And after that, as we said, each autoregressive loop has its own KV cache. Yeah. Say thinker is one autoregressive loop and talker is another. So autoregressive loops heavily rely on the memory on the KV cache. So we have to build different KV cache memory pools for those two models. So that introduced the last problems we tackled today is the memory isolation. And apart from the thinker talker's KV cache, there's other components like to encode audio into audio token and to decode audio token to realistic audio wave. There's still some neural networks that works in the scenario. So we still have to think about their memory requirements. So that's rather makes the memory layout complex. And that's the problems we want to figure out. So far, we have reviewed what kind of model we are optimizing on. Their characteristic is like not only one autoregressive loop. So there's more loops, more scheduler, and more stages. And the computing progress, we define it as someone is memory efficient, someone is computing bounded, someone is memory bounded, but the small components, those kind of small autoregressive loops, they are latency aware, but neither bounded by any of the memory or computing. And after we get the computing progress and model we are optimizing on, we are starting to building on the optimization. The first we think about is like scheduling. And the second thing we think about is like communication between the scheduler. And the last thing is the memory. Different schedulers should have different memory layouts and how we are tackling this. Yeah. I have used half the time. So are there any questions that I should are there any more questions? Yeah, if not, I can continue. Yeah. I think I will still have like 10 minutes to finish my talk. So is that okay? Yeah. Yes. Okay, cool. So the first thing is like we say scheduler decouple. As we said, a text model is encoding is purely by text tokenizer. So it is pretty simple. And right now for audio models and audio vision models, they have to using neural network to encode audio and to encode video. So we have to put the preprocess and the encoding a separate stage to facilitate it. So in this sense, we put 5 stage for Queen3 Omni. The first one is the preprocess. It's like wrapping up a batch to process to load the wave to the wave files and send it to the following parts. And the encoder, most of the time we encode the image and the audio. Note that image and audio encoder, they are neural networks. Okay. And behind this is like the thinker, is one autoregressive loop, and is use our Omni scheduler to make the scheduling process and manage the KB cache. And also the token and MTP part, we fuse them together and putting them together to get information from the thinker and run its own autoregressive loop. The token MTP autoregressive is a little bit different than traditional language models autoregressive loop, since the token MTP is input is like a think token and the hidden dimension of thinker, but we can still adapt SGLang's already established KB cache methods. And the final one is the code-to-WAV, is like the inverse of the encoder. Encoder is like to take audio into audio token, and the code-to-WAV is like added audio token back to the audio. Yeah, but indeed there are like some words like the codec token or codebook. We may not go so deep into that, but as we say, as we have put in more neural networks running together, we have to using different scheduling policy for each of them. Okay. And another thing is like the communication layer. The concrete example is like, as we said, in this figure, we fuse the token and MTP together. But why we have to do this is like starting from the communication protocol. If we split in this figure, if we split the token and MTP into 2 stages, we have to build up the actual communication layer between the token and the MTP. So they can either be using relay with ZMQ or using RDMA, but it still lags a little bit. And we say token and MTP is in a concrete loop, and MTP layer after its generation should send back what is generated to the token. So in essence, we tend to fuse the token and MTP together to make it into only one stage. So this so there no cross schedule overhead happens for the token and MTP, and note that thinker never need to get the information from the talker. So there's no backward information from the talker to MTP. So we put thinker and talker differently into 2 stage. So right now, the communication is quick from thinker to talker, and there's no need to communication from talker and MTP, and everything is good for our design. Okay. And one last thing is like the memory. Yeah, you can see where there we have a stage configuration, and we can put concrete memory configuration for the models to say what kind of thing you want to make it, like how much is the TP size and which do you want to use to. Yeah, and that actually helps us to isolate each stage's memory. And another concrete example I want to share is like multimodality is really memory consumption consuming. So take one example. Right now people use like language models every day, and language models most of the times they're purely text. Yeah, most times it's purely text tokenizer, and text tokenizer does not consume any of the memory. But if we are using Omni models to produce the video, input a 1 minute of video to the thinker shall create over 30 gigabytes at peak memory for the encoder if we do not do offloading or streaming or chunking. So that means the encoder is rather complex, and we should put specific place for the memory for the multimodality encoder to withhold to produce multimodality information, so as so far for the audio. Yeah. Yeah, and that's the notes for memory isolation. And so yeah, that's the 3 things I want to talk in concrete. So following the trend, we can take back. So this page shows what kind of model we are optimizing. Shift differently, like there's more autoregressive loop, and we should treat each autoregressive loop and the independent stage, but we're using stage communication to put them together. And other things like we discussed, given those kinds of models, what characteristic they have and how we should optimize and what should take in mind, and we should optimize that. And after that, we set three interesting points that we design. The first thing is the scheduler, and the second thing is like the scheduler communication, and the final thing is like the memory, given all those kinds of multimodal information and the schedulers. Okay, and here we show one by one our scheduler and our communication design and our memory isolation strategy. So that's all the information or the context I have today. Yeah. And the final page is we put Astralan Omni's roadmap. So in short, we should definitely embrace more models. As we see right now, the trust fusion or those kinds of interleaf generation model is getting to be more and more trending. So we are heading towards those kind of models. And the other things like we want to support cross nodes multi-stage pipelines is right now all those kinds of we are seeing a trend as this kind of model is getting to be bigger and bigger, as big as those kinds of language models. So we should have cross-node support still. And the other kind of things like the diffusion stage, like supporting diffusion like a stage machine into Astralan Omni. And also the and also we see the reinforcement loop for those kinds of Omni models. Yeah. And the production level serving those kinds of cloud infrastructure things. Yeah. And if you feel interested for those kinds of model and its characteristic, please feel free to join us and scan like the codes here, and you can go to our projects. Yeah. And thanks for the hosting today. And are there any questions for this?
Chenyang, that was a great talk with lots of interesting technical aspects for supporting this. I have the first question, and then I'll queue up the other questions that the audience have shared here. Have you seen any interesting use cases from SGLang customers for this particular feature?
You mean the project I'm making on?
Yeah.
Okay. I can share is like not from our customers since I cannot share the customer information, but I can share my personal utilization. I using the machine. I using those kind of techniques when I go to the market and to buy in, especially vegetables. So most of the times I do not know what's those vegetables, their name, their is. So I use my phone and as I said, I turn on the camera and I chat with it like Kun, could you tell me what's the vegetable it is? I mean, yeah. So that's one interesting thing I'm using. Yeah, it actually works really good. Yeah, especially when I was like buying. Yeah, another thing like was buying stack. So I'm not familiar with what kind of stacks they are. Yeah, I don't know how to differentiate like New York steak or Philly. So I just discuss with the model and this gets the video input and chat with me.
I see. So that's your personal use case there. So let me bring up a question from the audience, okay?
Okay.
So the question is, if we use a VOM that is used to modify prompt before sending things to a diffusion model, then is SGLang Omni good for that use case?
Sorry, I was quite not sure what the question is.
Yeah, I'm not sure about the modified prompt part.
I was thinking about like maybe you're thinking about some rumors like how the GPT image 2 is being made, like they have one model first to modify the prompt and then send the prompt to the diffusion model. That may be possible, and it's also some kinds we can also say this is some kinds of multi-stage models, but we do not. But right now there's no open source model that actually do this. And from my perspective, I understand that there's a lot of the I mean those kinds of something like the filmmaking companies, they are using diffusion models to generate short films, and they have a bunch of people working on prompts enrichment. They write prompts like 1,000 times more complex than us. So
I see.
to make it like fine-grained control the screen. Yeah.
Okay. All right. The next one is very interesting. So I'm going to bring it up and we'll love to get your thought on this. Essentially, because of your experience, which unsolved inference bottleneck do you think is valuable enough to become the next billion-dollar AI infrastructure company?
Fan, if I have that question, I'm gonna lead that company myself. Okay.
Exactly.
Yeah.
What's your thought?
Sorry to say that of course I do not have a really confident question. Yeah, but I have some possible solutions to the question. Like The first one, as I said, is the multimodality. I guess a lot of people has been watching Thinking Machines blog. I mean, the new model, the interactive model. I think that is one thing really interesting. And as I said, there's a lot of the model usage happens apart from coding. Not everyone codes, right? I mean, across the United States, well, I do not believe there are like 1% of the whole population codes, but at least everyone go to the market and to buy vegetables. So I think why I love those kinds of interactive models. Sorry, I mean the interactive models. Yeah, and that's one thing for the interactive or the kind of multimodality things. And also another thing I want to say is like there's a lot of company called the R&D companies. Am I right? Like the auto research companies. The final points for machine learning research, as I said, is like if we can make machine learning research automated by themselves, then humans are finished. I think that could be a great thing to working on. And this year, I have seen a lot of people, as I'm a reviewer for machine learning conference like NeurIPS or actually ML, right?
Self-improving.
Yeah, there's a lot of papers there, and they are demonstrating they are making self-improving agents, not self-improving research. But so far, I do not think they are great.
Got it. All right, so let's take 30 seconds for you to answer this question, and I think you will like this one. That was a great talk. Could you give some insights into how one can participate and contribute to SGLang?
1 year before, I may say welcome anyone, but right now I feel really hard to say. The first thing, like coding. I mean the cost of coding is really cheap. You can always using coding agents and maybe wrapping up tens of thousands of PRs and sending to the Astralan community. But that's not the good thing. So I think the first thing, I think there's only one thing keep in mind to contribute to any open source project. That is responsibility. Anyone should feel responsible for their PR. That these PR should, these PR should be responsible. But some ways, like first, you should know what this PR is making out, and the second, if this PR introduce some failure, you should solve it rather than say, "Oh, AI made this. It's not my business." No, you are submitting the PR, and you are the owner of that PR, and and the credit goes to you. So my answer to this question is like first, as long as you are responsible and has a long minds of contribution, reading the code base is really sounds easy. And right now we have coding agents, and it can help you codes and reads 100 times faster. And after that, after you get the basic dialogue of what the project is heading on, then it's your time to start building. And as we say, SGLang is massive projects. Possibly there's over 100 people working on SGLang. So you do not need to know all the people what they are working on to start building. You can start building something tiny and then when we're getting to the core, right?
Yeah. All right. With that, Chenyang, thank you so much for spending time with us this afternoon. Appreciate it.
Yeah, thanks. And
all right.
Yeah, thanks so much.